All right, so whoops, gotta go back a little bit. Okay, multiplying matrices. Okay, the product of two matrices, we're gonna take matrix A and matrix B, and we're gonna multiply matrix A times matrix B. Okay, it works. Here's the trick with multiplication. It's a little bit different than addition and subtraction. Remember that we said we can only add and subtract matrices that line up, that have the same dimensions, same number of rows and columns. It's different for multiplication. For multiplication, what we have to have is something kind of weird. We have to have the number of columns in the first matrix match up with the number of rows in the second matrix. Now that's easy to see if you write the dimensions out of the two matrices. So for example, if matrix A is a 4 by 3 matrix, that means how many rows and how many columns? 4 rows, 3 columns. You always say the rows first and then the columns, right? Rows, then columns. So 4 rows, 3 columns. If matrix B is a 3 by 5 matrix, those multiply because the number of columns in the first matrix matches up with the number of rows in the second matrix. So here's the rule you can always remember. When you write the product in order, and the order matters here, multiplication of matrices is not commutative. So now we're used to things being commutative when we multiply. 3 times 4 is the same thing as 4 times 3, right? But with matrices, that is not the case. A times B is different than B times A. And in general, what happens most of the time is, if matrix A multiplies by matrix B, then if I flip that around, matrix B will probably not multiply by matrix A if I change the order. So order is important. So if we write the dimensions of the two matrices in order, so it's matrix A times matrix B in that order, the inside numbers have to match up. There are always going to be 4 numbers, 2 numbers for each matrix that define the dimensions of that matrix. So the second dimension of the first matrix and the first dimension of the second matrix have to be the same numbers. Otherwise, they will not multiply. Okay? If those numbers do match up, then when we multiply the two matrices together and get our product matrix, we call it, A times B, notice that the first number, the first dimension, the number of rows of the first matrix, and the last dimension, the number of columns of the second matrix, end up being the size of the product matrix. Okay? See how that works? So the inside numbers have to match up, but as long as they match up, we can just cover those up, and we get the dimensions of the product matrix.
So that's all it is. Just if they don't match up, fill them out.
If the inside numbers match up, then ignore them, and the 2 outside extreme numbers are the ones that that are going to give you the size of the product matrix. Okay. So this is, remember, this we said it was a 4 row by 3 column. This was a 3 row by 5 column. And because the number of columns and rows match up, it multiplies. Okay, so we get a 4 by 5. So in general, this is what it has to look like. If matrix A has dimensions m by n, m rows, n columns, and matrix B has dimensions n by p, n rows, p columns, then they do multiply, and the product matrix has m rows and p columns. Okay? We can just stick it up. Okay, that just tells us if they multiply. Now, how do we go about the product of actually multiplying? Here's how it works. So let's take this example here. Matrix A has what dimensions? What?
3 by 2.
Everybody agree? 3 by 2?
Yeah.
You have a question?
How do you clear stuff out of your matrix?
I'll tell you the truth, I don't even know, but you never have to. You never have to, because as long as if you want to build, there's probably, if you go to the catalog, there's probably some weird function that clears the matrix. But anytime you want to build a matrix, you're gonna have to go in and edit it anyway, and so you'll just write over the top of the old one. Okay. Is there? Do you know how to do it?
No, you just have to enter in 0 for all those ones.
so I thought we would.
Oh, yeah, okay, maybe, okay, that might do it too. But there's no need to ever do that. You can just, every time you need to build one, just go start, just, you're gonna have to define the dimensions at the top anyway, and so it'll make that template. And you'll just put in the numbers that you want, okay? So A is a 3x2, what's B? 2x2, so do they multiply? They do, don't they? Because if I write those out, A before B, the inside numbers are both 2, so they match up, right? So they do multiply. And the resultant matrix is going to be a 3x2, okay? We know that's going to be the case. So how do we get the entries, or the elements, that fill up that product matrix? Here's what we do. We're going to multiply the rows of the first matrix by the columns of the second matrix. We're just going to, it's like we're going to overlap those numbers and multiply them. So think of it this way, visually. We're going to take this first row, we're going to peel it off, we're going to turn it sideways, okay? So, so that the first becomes the top and the last becomes the bottom, and we're going to stick it over the column that we're multiplying it by, and then wherever the numbers overlap, we're going to find those products. Okay, we're going to multiply those numbers. So then, here's what it would look like. There's A and there's B. If we want to find the row 1, column 1 entry for our product matrix, we're going to take row 1 from the first matrix and column 1 from the second. So the -2, if I peel off that first row, twist it, and stick it down on top of the first column, doesn't the -2 go with the -1? So we multiply those. -2 times -1 plus the 3 would go with the -2 then, wouldn't it? So plus 3 times -2. Okay, make sense? If I want to get the row 1, so that's, and in our final matrix, look, that's row 1, column 1. That's going to just be a number. Okay? If I want to get the row 1, column 2 entry for our product matrix, I'm going to overlap row 1 with column 2, right? So if I, once again, take that first row, twist it, stick it on top of the second column, the -2 goes with the 3 this time, right? And the 3 goes with the 4. See how that works? Okay, if I want to get this one, if I want to get row 2, column 1, go ahead, see how that works? Those numbers go with each other. Those numbers go with each other. Okay, and I'll make sure this PowerPoint's up there so you can go through this at home if you want. If I want to find the row 2, column 1, I'm going to take row 2 of the first matrix, column 1 of the second matrix, and overlap those. Yes, sir?
What happens if the row and the column didn't, like they weren't both 2 rows?
They have to, because remember we said in order for matrices to multiply, those inside dimensions have to match. So that means they'll always have the same number of items in a row and a column.
So if they don't match up,
They won't multiply. Yeah. Okay. And then if I want to find row 2, column 2, I'm just going to superimpose, row 2 with column 2, etc. I just work my way down like that. Okay. So it's kind of a tedious process, but that's how you multiply out a matrix. And then once I take all those numbers, if I just simplify all that, I'm just going to get an answer that looks like that, right? I'm just going to get 6 numbers, 3 rows and 2 columns worth of numbers, okay, in that array. All there is to it. Okay, now, as I said, matrix multiplication is not commutative. There are a few things you can do. When we're multiplying matrices, it is associative. So if I'm multiplying 3 matrices out, it doesn't matter the order in which I have to leave them in the same places. So A has to come before B, which comes before C, but I could choose to multiply those in any order I want to. I could either multiply the first 2 together, get a product matrix, and then multiply it by the third, or I could take maybe the second 2, multiply those together, and then multiply the first one by that result. But I can't change the order. Left and right order has to always stay the same with matrices. Okay? And then I can distribute from the left. But notice if I'm multiplying A times the quantity B plus C, where these are all matrices, the A has to stay on the left. If I'm distributing from the right, that's also okay, right? I could distribute the C from the right, but the C has to stay on the right when I write those products out. That left to right order, you can tell that's really important. You can't tweak that. And then if I'm multiplying a scalar like we did yesterday, just a number times the whole product matrix, I could multiply that either by the first matrix, A, and then multiply by B, or I could multiply that number by the second matrix. Doesn't matter. Doesn't matter how I do that. But when you actually do problems with those, it just makes sense, that scalar stuff. Okay, here's one quick example of why this is so useful. Other than the stuff we're going to be doing later on in the chapter, there are some applications where matrices are extremely useful. Like here's one. In business applications, if we've got some inventory of items and we have the cost for each of those items, cost per item, I can build those into two separate matrices and I can easily find total cost this way. So for example, let's take this. The inventory matrix is going to be M by N. The cost matrix is going to be N by P. Then I'm going to end up getting a total cost matrix that's M by P. And our example is going to look at, one other thing. You got to make sure that the labels match up. So, and you'll see what that means in a second. It really is helpful when you're building these matrices if each row has a certain label and each column has a certain label. And you got to make sure that the column labels in the first matrix match up with the row labels in the second matrix. It'll totally make sense when you see an example. Here's what we're going to do. We're going to add up the cost of a bunch of equipment. We got a women's and men's softball teams, and we're going to have to buy bats and balls and uniforms. Okay? And here's what we know. The bats cost $21, the balls cost $4, and the uniforms cost $30, right? So we're going to set up an inventory matrix, and then we'll set up a cost matrix. Okay. So here's what the inventory matrix would look like. Okay, we've got the various items of equipment, and then we've got the two different teams, right? And that's just what they were, right? That's how much of each item we're going to buy for each team. That makes sense. Just like a spreadsheet. Okay, here's the cost. I have to make sure that I've got the items that we're purchasing head the columns of the first matrix and head the rows of the second matrix. Because remember, the columns from the first have to match up with the rows from the second, right? Okay, and we knew that those were the costs of each of those items. Now look what happens if I multiply these out. If I multiply these matrices, I'm going to end up with an answer that's going to have women's team and men's team. Those are going to be the row headings, and the column headings are going to be the costs for each of those two things in dollars, right? We know that as long as the columns from the first matrix match up with the rows from the second matrix, they just disappear, right? And the answer is just going to be this stuff, that and that. And look what we get. If I just do the math and I multiply those matrices out, that's what I'd end up getting, right? I'm going to superimpose the first row, twist it, put it over the column. There's only one column. So I get row 1, column 1. I take the second row, twist it, put it over the column, and I get the second row 2, column 1. I only get two entries, 882 and 977. But that's important because those are the dollar amounts for the women's team and the men's team. Okay? See how that works? All right. Now, how do you do it on a calculator? As expected. Let's just go back and look at one quick example. Break out your calculators. Why don't we just do this one that we were just looking at? Okay, if I want to do that product on a calculator, what do you suppose I do? What do you suppose I do? Yeah, okay, I've got to make a matrix A and a matrix B. That'll be A, that'll be B, right? So I get there by second matrix. Now what? Edit. Okay, so I'm going to edit A, and I want the dimensions of A to be what? There's matrix A. No. 2 2 by 3, number of rows by number of columns, right? So I'm going to go 2, enter, 3, enter, and it'll build my template. And now, Andrew, you see what I'm saying? Now you just write the numbers in there that you want. There's some numbers already in there, but we'll just write over the top of them. So I'm just going to hit 12, enter, 45, enter, 15, enter, 15, enter, etc. Okay, so there's the first one. I can go back second, matrix, edit, 2. So I got to edit B. What's B going to be? What dimension is going to be of B? 3 by 1. Okay, 3. And then I've just got 21, enter, 4, enter, 30, enter. And now what? Okay, I'm not going to go back to I'm going to go back. I'm going to quit the whole thing. This is kind of important. I got to quit and go up to my home page because that's where I'm going to do the arithmetic. That's where I'm going to add them up. Now I got to go to matrix. Once I'm on the home screen, I need to put a matrix A there, right? I wonder if there's a shortcut to that. Let me just look real quick and see. Yeah, there is, right there. Look at that. There is a shortcut. If I go alpha F3, oh my gosh, look at that. I didn't even know that was on there. Huh. Okay, let's not use that for now, though, because I'm not sure how to use that. Well, I'll figure it out and tell you about it, but oh well. So, get out of there. Clear. There we go. Okay, so I'm just going to go from the home screen. I just go second, matrix, what? A. Okay. Matrix A times second matrix B, right? And there's my answer. Sweet. Let's do it. What's that? Yeah, that's a lot quicker than I agree. Okay, 332.